So this is question number 7. What are the carbon Y hydrogen or carbon Y carbon bond angles in each of the following compounds? And it says here that Y stands for non-metal. So those are common abbreviations in organic chemistry and actually inorganic chemistry. So these would be common abbreviations. Y stands for non-metal. X means halogen atom. Non-metal atom. So let's be fluorine, bromine, or iodine. And finally, M stands for metal. Those are common abbreviations. Maybe I should put them under question. So that does interfere with the answers. Okay, so we are looking at these angles. And that's actually related to chapter 1, and then we repeat that at the beginning of chapter 3 when we are looking at properties of compounds. That's also similar to question number 1, where I said it's really chapter 1, but it's related to chapters 2 and 3, what are right here, what is the hybridization. So in this case, we are looking for carbon, oxygen, carbon, or because it's carbon Y, hydrogen, carbon Y, carbon. So it's carbon Y, where oxygen is the only non-metal. Here you're looking at each, which one is non-metal, other than carbon and hydrogen. Y, X, M, that all means other than carbon and hydrogen. So what's this angle? Well, this is oxygen with two substituents. So it's sp3 hybridized oxygen. And if it's sp3 hybridized, then it's a tetrahedral bond angle. Now, tetrahedral bond angle is 109.5. So you may want to consider that. Let me see if I can insert the degree sign. Yeah. 109.5. So if you have angles listed under in multiple choice question, you may want to pick this one because it's tetrahedral. But with oxygen, there is deviation from ideal tetrahedral bond angle due to free electron pairs, but also in this case, it's going to be due to steric hindrance. So for oxygen in water, it was 105. Here, because these are larger substituents than hydrogen, angle is going to be open up a little bit. And so it will be something specific for this compound, tertiary butyl methyl ether. I would stick only to these two. It's tetrahedral or 109.5. Next one. So we are looking for carbon, oxygen, hydrogen. That's CYH. By the way, all these angles are shown as 90 degrees. That's typically how we show them in Lewis formulas. To prevent you from guessing what is the angle, just by looking at inspecting the formula. And seeing, because we try, when we draw line formulas, sometimes we try to be as close to actual angle as possible. So here, what do we have here? We have oxygen as the central atom. So again, what are these two angles? Carbon, oxygen, hydrogen. And so now oxygen is actually sp2 hybridized, because you can see it forms double bond. So there is one pi bond. So it's sp2 hybridized. sp2 hybridized atoms have trigonal planar bond angle. Okay. And trigonal planar is 120, close to 120. Actually, it's almost never exactly 120, but it's approximately 120. So that's the best approximation. So if it's a number, then it would be 120. We would typically say tetrahedral trigonal planar, but if you have to guess a number, you would say about 109.5, about 120. And on the test, I would probably accept either one. If you are typing this up, then I would expect you to type up on the test 109.5, and you don't have to bother with degree sign. Same goes 120, don't bother with degree sign. Don't bother trying to find where degree sign is in those menus and so on. So here, Y is nitrogen. So carbon, nitrogen, hydrogen, either of these two, carbon, nitrogen, hydrogen. So what is this angle? Well, nitrogen is, again, sp3 hybridized, just like oxygen. By the way, you're supposed to know how many free electron pairs are on each atom. There are, for example, 2 free electron pairs on oxygen. They may or may not be shown. There is 1 free electron pair on this oxygen, 1 free electron pair on the nitrogen. How would you know that? They are second row elements, and they have 8 valence electrons. So here, 1 double bond, 1 bond and 2 bonds. So that's 2 bonds. That's a total of 4 electrons. Octet, 8. Oxygen must have 8 electrons. It's missing 4. It's missing 2 free electron pairs. They are not shown. Here, oxygen forms 3 bonds. 1 double bond and single. Total of 3 bonds. 6 electrons. Up to 8, 2 electrons are missing. 1 free electron pair. Nitrogen forms 3 bonds. 6 electrons. 2 are missing up to 8, so it has 3 electron pair. For each charge, positive or negative, you should add or subtract electrons from ground state. So, well, actually, in this case, maybe you shouldn't really bother. I don't want to really introduce that part of concept. That's actually for formal charges, for calculating formal charges. A little bit different concept. But anyway, so for oxygen, for example, here formal charge, this oxygen is +1. The reason why it's +1 is free electron pair, 2 electrons. And then 3 electrons, 1 from each bond, that's 5. So oxygen, we assign in this case to oxygen 5 atoms, 5 electrons. 3 from bonds, 1 from each bond, and 2 free electron pair, 5. And it has 6 in ground state as oxygen atom. It has 6 electrons. So for positive charge, we subtracted 1 from 6, that's 5. So that's another way to find out number of free electrons. It should have 6 with positive charge. It should have 5, 3 bonds, 1 from each bond, that's 3, 2 are missing, so 1 electron pair is missing. Nitrogen in ground state should have 5, 1 from each bond, that's 3. There are no charges, therefore 2 are missing, and that's 1 free electron pair. So this nitrogen is sp3 hybridized. Again, no double bonds, no pi bonds, sp3 hybridized nitrogen, and that means tetrahedral, just like the first one. And the last one, so carbon, nitrogen, hydrogen. Now we have triple bond. Triple bond means 2 pi bonds. So hybridization of this nitrogen is sp3 minus 2 for 2 pi bonds. So 3 minus 2 is 1, so it's actually sp hybridization. And sp hybridization means linear. Okay, let's look. Yeah. And when it comes to angles, linear is always 180. It's not approximate, it's not close or anything like that. It always is 180. Let me try to do it a little bit. Well, it's as close as it gets. Okay. So this question also could have been about number of free electrons. Here would be 0 free electrons on nitrogen. It has full octet, 4 bonds. So that's full octet, 4 bonds, 2 electrons from each bond. That's 4 times 2, 8. That's it. Or if you're looking, if you're using formal charges +1. In ground state, nitrogen has 5 electrons here, and positive charge, that means here it should have 4 in the outer shell. 1 from each bond, 4, everything is represented, 0 free electrons. Okay, this was a little bit longer one, so let me check if there are any questions before we move on to a little bit different topic of intermolecular interactions. Is oxygen sp2 because there is pi bond? Yes, that's correct. 1 pi bond sp2, 2 pi bonds sp. How did you know to base tetrahedral of the carbon in 3 instead of nitrogen? Actually, no, it's nitrogen is tetrahedral, it's not carbon. In third example, it's the nitrogen that is tetrahedral. That's what you're looking for. You're looking to that central atom Y. So what is geometry on the central atom Y? And that's nitrogen. So nitrogen is tetrahedral, and so nitrogen has tetrahedral geometry. So each of those, CYH, CYC, you are looking for geometry of the atom Y. That means atom on, what is geometry on oxygen? Oxygen, nitrogen, nitrogen. So this oxygen is tetrahedral, this oxygen is trigonal planar. Carbon is also happens to be trigonal planar, but we're looking at oxygen. Nitrogen is tetrahedral. All these carbons are also tetrahedral, but we're looking at nitrogen. And this nitrogen is linear. This carbon is also linear, but the question is about nitrogen. Okay, hopefully that answered your questions, and let's move on to question 8. What is the strongest intermolecular interaction present in each of the following compounds? So you go one by one and identify type of intermolecular interactions. Typical intermolecular interactions are London interactions, dipole-dipole interactions, and hydrogen bonding. So in this case, we have an ether. Ether is polar compound. So hydrogen bonding would be present in compounds that have bond that is YH, where Y is nitrogen, oxygen, or fluorine. So for hydrogen bond, you must have YH. We don't have OH, NH, or FH here. So we eliminate hydrogen bonding. And then we look what kind of compound is this? Is it polar or non-polar? If it's polar, dipole-dipole interaction is present. If it's non-polar, then only London interaction. Ethers are polar because of the presence of oxygen and 2 negatively charged free electron pairs on oxygen. So if it's polar, that's dipole-dipole. Of course, weaker London interactions are also present. So we could list dipole-dipole and London, but in this case you wouldn't list them because the question is what is the strongest? And so you're only identifying the strongest interaction. Next compound only has carbon-carbon and carbon-hydrogen bonds. Those are non-polar bonds, and since compound has only non-polar bonds and there are no free electron pairs, it can't possibly be polar. And of course, it doesn't have any NH, OH, FH bonds. So those are London interactions. London is, of course, capitalized because it's named after Fritz London, German physicist. Next one, sometimes students are a little bit confused by it because they see a charge and then what's going on charge. It doesn't matter. You have OH. OH and HFH, hydrogen bonding. Next, we have this CN. Double bonds are much more polar than single bonds, and triple bonds much more polar than double bonds. And this is obviously polar bond. Remember from previous class, you are looking at electronegativities. That's why you will have a list of electronegativities on the test. So if polarity between two compounds that are bonded to each other, two atoms that are bonded to each other, if difference in electronegativities between two atoms that are bonded to each other is 0.2 or greater, that's polar bond. Since this is triple bond, it's even more polar than double and more polar than single. Even single is polar enough to be polar. But this is very polar bond, so it's highly polar compound, and of course, then this is dipole-dipole. We don't have NH, so dipole-dipole. And I just answered next question. Same compound, but this free electron pair. Remember, there is free electron pair on nitrogen. If we are looking like previous question, are there any free electron pairs? Nitrogen must have 8 electrons in the outer shell. 3 bonds, 2 from each electron. That's 6. It's missing 2. There is free electron pair here. This electron pair could be used to be bonded to hydrogen. And now we have this ion. This ion exhibits hydrogen bonding because we have an H bond. For hydrogen bonding, ignore plus minus. The fact that something is ion or even free radical doesn't matter. If it's OH, NH, that's hydrogen bonding. Again, as organic chemistry course progresses, questions and concepts get a little bit more and more complex. So I'm going to stop again to see if there are any questions. For number 7 in the third diagram, what's that? How is it tetrahedral instead of trigonal planar, trigonal pyramidal with low pairs, lone pairs? Actually, strictly speaking, it is trigonal pyramidal, but tetrahedral is the shape of the electron cloud. So that's kind of in the first approximation. So if you look, let's let me see, what is the page? Oh, it's chapter 1. Yeah, that's Vesper theory, I think. Yeah. Okay, so um, I wonder if I fixed that. I thought I did. Okay, so it's page 28 in the textbook. Let me just see what is exactly. I forgot what I put in the textbook. But the shape of you're looking for the shape of the electron cloud. So shape of the electron cloud could be linear, trigonal, planar, tetrahedral, and so on. So in the shape, like you see, if you look at this shape of electron cloud, like this one, I'm not showing it. So for this one, shape of the electron cloud, try to, it's a little bit small. There it is. Okay, so for these, shape of the electron cloud in each case is tetrahedral. And so, actually, no, I'm pointing at the wrong one. Yeah, I'm pointing at the wrong one. Okay, it's in the line. Okay, so, there. Okay, so because I can't see both the book and this is very small screen attaching. So 4. When you have a total of 4 electron pairs, that means bonds and free electron pairs, then shape of the electron cloud is tetrahedral. And so in each of these cases, you consider tetrahedral shape of the electron cloud. So in this row, it's all tetrahedral shape of the electron cloud. But for the shape of the molecule, we ignore electrons. And then you have different shapes of the molecule. You have tetrahedral, trigonal pyramidal, or bent. But in each case, bond. So something y something, something y something, something y something. Bond is always approximately tetrahedral, close to 109.5. And so that's why we classify that as tetrahedral. And then this one, we would all classify shape of the electron cloud as trigonal planar. And with 2, you would always classify that as linear. So it's different. So we're looking at particular angle, particular bond angle. If you're looking at the shape of the molecule, then we would use terminology that you're talking about. We would say molecule is trigonal, planar, or bent, or something like that. But for the actual bond, just CYH bond or CYC bond, then we would look, is it a tetrahedral bond, trigonal planar bond, or linear bond? Hopefully that makes sense. Okay, and I don't see any more questions, so let's go back. Okay, question number 9. What is the strongest? This is question number 9 is more advanced. And by the way, kind of a funny thing, when I used to give this question, it's advanced question. It's, if you see it on the test, don't be scared. Sometimes when I say that, I kind of regret saying it's advanced question. It's more challenging. And then some students don't even bother. Okay, okay, this is a difficult question. I'm not that good. No, of course you should put your effort into it. Just because it's more difficult than the previous one doesn't mean you shouldn't be able to do it. But what is funny thing is when I used to give this as write in as paper test, this is obviously write-in question. The student is supposed to write here what is each type of interaction. And I would give a student who would, for example, circle a C, and that's it. So, that's sort of funny. It's sad that student doesn't have that much knowledge that could even put something like that answer C. That's completely meaningless. But that's unfortunately the way things are. So, what is strongest intermolecular interaction present in the following mixture? So, this question could be asked in two ways. So this is the first one. And actually, maybe I will copy and paste for the second type. So let's look at the strongest. So when you're looking at the strongest, that's actually a more difficult question. Then you look first. You have water and ethanol as a mixture. So among water molecules, what are possible interactions? Well, strongest interaction among water molecules is hydrogen bonding. So that's it. Ethanol, also hydrogen bonding, it's alcohol. And then if water and ethanol interact with each other, it's also hydrogen bonding. So in each case, it's the same one, hydrogen bonding. Just put hydrogen bond, and that's it. Okay. Now next one, hexane and diethyl ether. So hexane is non-polar. So the strongest interaction is London interaction. That's it. There is nothing stronger than that. Diethyl ether is polar, but no hydrogen bond. It can only be dipole-dipole. So now we have hexane, which is London, pretty weak, diethyl ether, that's dipole-dipole. And what if we mix the two? What is interaction between the two? Well, the interaction between the two is dipole-induced dipole. But dipole-dipole is stronger than dipole-induced dipole, so you would list it as dipole-dipole. So you see, in this case, you have to consider each time three sets of interactions. Interactions between each of the separate compounds and among the molecules of hexane, among the molecules of diethyl ether, and between hexane and diethyl ether. So next one, diethyl ether, polar, dipole-dipole. Dichloromethane, among dichloromethane, it's also polar, it's going to be dipole-dipole. And two different types of polar molecules, also dipole-dipole. So it's the same as before. Strongest interaction is dipole-dipole interaction. And the last one, sodium chloride and water. In this case, actually, you have to know this. It's from the end of the chapter. This is ionic compound dissolved in the polar solvent. When ionic compound is dissolved in polar solvent, crystal lattice of ion is split into individual ions. And then each individual ion interacts with dipole of the solvent to give ion-dipole interactions. These are very strong interactions, stronger than pretty much anything else you would encounter. And so there is nothing to think what between sodium chloride and water. It's ion-dipole. When you have ionic salt, ionic compound, and polar, dissolved in something polar, and actually ionic compounds are only soluble in polar substances, then it's ion-dipole. And actually, let me just do one more. Okay. This is, okay, I can't even spell methanol. This is also ion-dipole. So ammonium bromide. This is also salt. Don't be confused. Or actually, let's say tetramethyl. Let's make it organic. Tetramethyl ammonium bromide. So let's make it organic compound because there are organic salts. Like quaternary ammonium salts are organic salts. Those are also ions. It's ionic compound. Okay. Let's do first 4 because E is going to be the same. Okay. So what is the strongest intermolecular interaction between the molecules of solvent and molecules of solute in the following mixtures. So in this case, you're not considering the strongest interaction overall. So when something is dissolved, when one substance is dissolved in the other, and in this case, it doesn't matter which one is solvent, which one is solute. But when one substance is dissolved in the other, then you have two pure compounds. In each compound, intermolecular interactions between those pure compounds, those molecules of the same species, are broken. And then new intermolecular interactions between molecules of solvent and solute, those different molecules, are formed. And so question here is those new interactions between those different molecules. What is the strongest interaction in each case? And so water and ethanol, that's again hydrogen bond, because water and ethanol form hydrogen bond. Hexane and diethyl ether, that's dipole-induced dipole. And that's because hexane is nonpolar, diethyl ether is polar. If polar and nonpolar species are miscible with each other, then polar species is dipole. And in the neighboring nonpolar species, it will induce dipole. It will attract its electron pair or repel electron pair towards itself, depending on which part of the dipole interacts, which part of dipole of diethyl ether, positive or negative, interacts with hexane. It will distort its electron cloud to induce dipole in hexane. And then interaction will be between dipole of ether and induced dipole of hexane. So those are dipole-induced dipole interactions. Diethyl ether and dichloromethane, since both are polar, and between polar molecules interactions are dipole-dipole interactions, no change, is going to be dipole-dipole. And here we have just covered that sodium chloride and water, ion dipole, between ions of sodium chloride and water dipole. I can put here actually, just to be different, tetrahydrofurane. It's also dipole, and let me show you, I will just post it in a minute, what is tetrahydrofurane. It's common organic solvent. It's an ether, and it dissolves polar substances. It's also known by abbreviation THF. So that's common organic solvent. You will encounter it a lot in the course, so you might as well learn about it now. Okay, so let me see if there are any questions. Okay, no questions, so let's go back. And then next one, arrange the following compounds in the order of increasing boiling points, from the lowest to the highest. So you have trimethylamine, butanol, and butane. You may want to draw these compounds, and sometimes there is, I intentionally write it this way, and actually butanol, I can put, let's say, 2-butanol. So that it also tests not only do you know intermolecular interactions, but do you know nomenclature. Some of you may be able to pick it out and figure it out from the names, but it's a good idea, particularly if you have the time to draw these compounds. So I'm just going to draw them quickly. Hmm. Okay, formulas coming up. So good idea to draw them. And next, boiling points are measure of the strength of intermolecular interactions when compounds are about the same size. And that means that you should figure out what is the strongest intermolecular interaction in each case, and then arrange them in the order of strength of intermolecular interactions from weakest to the strongest. And so as you go about each of these, this is, now I showed free electron pair here, I didn't show it here. So trimethylamine. This one on its own is capable only of dipole-dipole interactions. Trimethylamine with water could form hydrogen bond, see. But in this case, just dipole-dipole. Uh, 2-butanol or any butanol, 1-butanol, 2-butanol hydrogen bond. And of course, butane having only carbon-carbon and carbon-hydrogen bonds is non-polar, only London interactions. And so you know that strength of intermolecular interactions is, this is how you would answer the question. It's London, then dipole-dipole, then hydrogen bond. But you're supposed to arrange these compounds. So you would write it butane, then higher boiling point is that of trimethylamine. Note that in amines, actually trimethylamine, yeah, we don't separate substituents from the rest, from each other, and then 2-butanol. So this would be correct answer. Okay, so that completes test 3 review.